Chapter 12, Introduction to Analysis of Variance, Part 4. In analysis of variance, the F ratio is constructed so that the numerator and denominator of the ratio are measuring exactly the same variance when the null hypothesis is true. Recall that the null states that mu1 is equal to mu2 and that's equal to mu3. Of course, that's given we have three different populations or three different treatment conditions that we're comparing. So again, the null states that there is no treatment effect, that we will not see any differences in scores between these populations, which are being tested using sample data. Consequently, in this situation, we expect the value of F to be around 1. So as illustrated in previous video, again, if there is zero treatment effect, this is equal to 0. And then if we look at the second variable, the random unsystematic factors, if you divide anything by itself, it's equal to 1. So again, F ratio equal to 1.00 is representative of the null or provides support for the null, indicating that there's no treatment effect. If, however, we obtain an F ratio that is much greater than 1, then it is evidence that the treatment effect does exist and the null hypothesis is true. However, we first need to define precisely which values we would consider to be centered around 1 and which ones are much different than 1. And to determine this, we're going to evaluate and look at the new F ratio distribution. But before we examine this new distribution in detail, we should note two obvious characteristics. Because F ratios are computed from two variances, the numerator and denominator of the ratio, F values always are positive numbers. Remember that variance is always a positive value. Next, when the null is true, the numerator and denominator of the F ratio are measuring the same variance. In this case, the two sample variances should be about the same size, so the ratio should be near 1. In other words, the distribution of F ratios should pile up around 1. So again, as I illustrated here, zero treatment effect plus whatever the random systematic factors variability is equal to, divided by itself, is going to produce a value close to 1. With these two factors in mind, we can sketch the distribution of F ratios. The distribution is cut off at 0, all positive values, and piles up around 1. And then tapers off to the right, so again it's positively skewed as illustrated here in figure 12.7. We should note that the exact shape of the F distribution depends on the degrees of freedom for the two variances in the ratio. And in fact, based on the information in this previous slide, we will learn that the table of F values is organized by two DF values. The DF for the numerator, which is in reference to the between variability, and the DF in the denominator, which pertains to the within variability. So again, the exact shape of the F distribution is contingent upon those DF values. In fact, we can recall that the precision or accuracy of the sample variance depends on the number of scores or the degrees of freedom. In general, the variance for a large sample, large DF, provides a more accurate estimate of the population variance. Because the precision of the MS values depends on DF, the shape of the F distribution also depends on the DF values for the numerator and denominator of the F ratio. With very large DF values, nearly all of the F ratios are clustered near 1.0. With smaller DF values, the F distribution is more spread out. As previously stated, for analysis of variance, we expect F to be somewhere near 1 if the null is true. So again, we're talking about values centered around here. So therefore, we need to separate the values that are considered to be close to 1 and those that are significantly different from 1, or greater than 1, I should say, since it's positive. We're going to have always a numerator value greater than the denominator if we do see a treatment effect. The critical F value will be determined by the alpha level set for the hypothesis test and the degrees of freedom. And the degrees of freedom are referred to as degrees of freedom for the numerator and the degrees of freedom for the denominator. So given our F ratio, we know that the equation is equal to MS between over MS within. And consequently, the degrees of freedom for between would be considered the degrees of freedom for the numerator, and the degrees of freedom for within would pertain to the degrees of freedom for the denominator. So we're going to need to make that distinction when we enter the new F ratio distribution, as well as needing to know the alpha level that we are testing at. So given the previous example of the telephone conditions, we had 3 treatment conditions. So our K was equal to 3. So degrees of freedom between, or we would refer to it as degrees of freedom for the numerator, would equal 3 minus 1, and that's equal to 2. And we had 15 scores across treatment conditions. We had 5 scores per treatment and 3 treatment conditions. So our N was equal to 15. So the degrees of freedom for the denominator would equal 15 minus K, which is equal to 3, and that gives us 12. So we're going to cite degrees of freedom equal to 2, 12, and we're going to use both alpha level at 5% and 1% to see how we came up with these critical F values noted here. So here we have a portion of our F distribution. Again, the positively skewed shape of this distribution is noted here. And we should read this text here. It indicates that the critical values for 5% level of significance is in the light phase type, and the bold phase type pertains to alpha 0.01 or 1%. And notice the other components of the table. Here we show DF for numerator and DF for the denominator, and that's how we're going to enter this table to find our critical F values. So we had noted that our numerator degrees of freedom was equal to 2, and the denominator was equal to 12. So we're going to enter it at 2 here, and enter it here at 12. And note that both of these, one is for alpha at 5%, so our critical Fs. So alpha at 5% and our alpha at 0.01 or 1%. So we would cite 3.88 and 6.93. And now we've established exactly or precisely what we would expect if the null were not true, what F values have been set as illustrating treatment effect. And so again, before I move on, again, this was obtained by the intersection of these values, these degrees of freedom for the numerator and the denominator. So here we see where the critical region has been set using these critical F values that we just found in our F distribution table. Therefore, for this particular test, our F ratio would have to be greater than 3.88 if we applied alpha of 5%, and it would have to be greater than 6.93 if we used alpha of 1%. So again, this blue shaded area denotes the critical region. And if our F value fell anywhere in this region, then we would conclude that we cannot reject the null hypothesis. And again, the null stating that all of the means are equal to one another. And if we did see any differences in the mean, those differences or variations would simply be due to chance or explained by chance or sampling error. Again, that's if it falls in this area here. Again, that area is then considered close or near 1, and these critical F values have now established what we would consider to be significantly different from 1. And that concludes this video lecture on the elements of the F distribution. In the next video, I'm going to actually walk you through an example from beginning to end using the 4-step hypothesis process that we learned back in Chapter 8.